reasoning for this is pretty straightforward. Raise your hand if you've built a UI in Erlang. Yeah, really? You poor soul. Don't do that to yourself. Like, Erlang doesn't work on phones, on smart devices, even to a certain degree on personal laptops. And there's a very well-developed ecosystem already existent for those things. The Swift ecosystem is wonderful. And we have built something that makes Swift look and feel like Erlang and can be interoperable as a full-service Erlang node running perfectly natively in Swift. So we can bring Erlang into a new ecosystem. This is like the immediate thought, I think, that we all have about this, right? Like, we're having a re-implementation of Erlang, and we are going to do it wrong, right? We always do it wrong. Yeah, I don't know. Come you look at our source code. We're doing okay. The thing we're trying to balance here, we want all of Erlang's API. We want OTP, we want gen servers, we want individualized processes, we want that state management system that Erlang has that is so beautiful. And we want to retain, as much as we can, Swift's existing concurrency architecture. It's very well optimized for something that is different than Erlang scheduler is optimized to do. Like the key example is that Swift heavily prioritizes user interface actions, right? Something that's supposed to update the screen always goes first. And Erlang doesn't have as robust a system for that, right? So we haven't re-implemented Erlang scheduler, and we wouldn't do that. Instead, we're taking the abstract patterns from Erlang and the API implementation of those things and sticking it in the Swift programming language. And it's been quite successful so far. Swift has been, even in recent years, has built a new concurrency architecture that they're calling Swift concurrency. I loved May's talk. It pointed out perfectly, managing big concurrent systems is a huge issue across all languages. And we are, as a coding industry, trying to develop semantics and syntaxes and patterns that will work for that. And the classic one that you see everywhere these days is what I've been seeing called core routine concurrency, right? Which is that you have async and await everywhere, and any synchronous block, that's a core routine, and it can call out to asynchronous blocks and come back. And I don't think I need to tell you what that's good at and what it's bad at, right? It's great for very simple things, right? You have one thread that's going to live a long time and take a lot of actions and seed those actions to other threads. But when you have a more complex concurrency model, and you always have a more complex concurrency model, build this simple tree-type concurrency model in something using an async and await core routine type syntax. It's not easy to do. You get what people have called for years pyramids of doom. We like Erlang. We're here. Mm-hmm. We have built something that can do this and do it very well in Erlang, and we think it works amazing for building a good separate UI as well. Yeah.
Okay, so it comes in two parts, SwErl does. We've got the base part, and then we've got the node part. And you can see here how they're broken out in the way we are organizing the code. You see what our intention is to create over on the node side. Currently, not everything over there is working. Everything over on the left-hand side is. We are doing some potential optimization over on, sorry, yeah, your left. Your left-hand side. Yeah, we're doing optimization over there right now. We could have pushed to have a more complete version of the node side, but decided that good engineering trumped good presentation. So we do have a functioning EPMD, and we do have a hacked together version of the handshake between nodes. And we're re-engineering that right now. So.
Yeah, absolutely.
So we think we've done pretty good on our timings for having we've spent zero amount of time on speed, zero. And just trying to get everything laid out. And so we want to go back and see if we can get some better speed. But we think we've hit a pretty good spot here for our first cut. 17 ten-thousandths of a millisecond to spawn something is not bad. And statistically, the calls, whether they are stateful or stateless, there's not a statistically, I can't say that word today, statistically significant, there we go, difference between stateful and stateless. And so we just put these numbers up here. And, and 140 bytes even on a phone isn't that much.
They can be smaller too.
Yeah, it can, in some instances it can be. But it's pretty good for our first cut, we think. So what we're going to do, we wanted to give you that background, but we want to spend most of our time, right, we write code, so we want to see code and we want to see it working. So I threw together on Saturday a demo, and this is what's going on. This was actually an interview task for my first job writing code. So I'd applied to work for a simulation company, and what we needed to do as part of the interview process was to simulate two people standing at a table, and that's these two people here, standing at a table. Product is coming in. Okay. Product's coming in, it's raw product. They're going to put it in a box. They're going to take the box. As soon as it's in the box, they're going to walk it out to the loading dock and set it on the dock. Then they're going to come back and they're going to box another piece of product. Then a truck's going to arrive. And when the truck arrives, they have to stop boxing, go out and fill the truck. And each truck leaves when it's full or when it has reached its leave time. And then the task was to track the statistics on, how much time are they spending doing this and that, and how full are the trucks, and how much delay has been added because product can't move, and those sorts of things. We decided to keep it a little smaller and just focus on the two workers here. But you can see over there on the left, I've color-coded the types to match what we are doing inside this simulation. If I was writing this simulation professionally, I would do it a little differently, but we kind of wanted to show all the piece parts. So that's what we're going to see. So I'm going to step in here, and I'm going to show it running. Excuse me. So this is running on my phone. This is not a fancy pants new phone. This is my iPhone 11. And neither is the machine that this is running on, the Xcode and stuff. The numbers don't come off of a fancy pants machine either, okay? All right, so here we go. So initially, ready, set, go. So I've chosen just to update the view every 2 seconds, just because I wanted to do that. The blue represents them walking back and forth doing deliveries, and the green represents their boxing time. When a truck does show up, you'll start seeing orange at the top of each of these stacked bars. And I don't know when the truck's going to show up because it's on a random distribution. There it goes. The truck has arrived, and now they are boxing. Still boxing. And again, the leave time is also on a distribution, so it might be longer time and it might be shorter time. We don't know.
Could field some questions while we watch the bars.
Well, it might happen any time. Say that again?
Why is the truck not fitting up?
Because the truck only reports its leave.
Full percentage.
Yeah, percentage of full when it leaves.
That's fair.
This one will be larger than some. Some of them have been leaving at like 20% full because they have a shorter leave time than the others. But yeah, we can Looks like it's going to be a long one this time. So there is no simulation clock involved in this simulation. That's another interesting thing. So there's no tick going on there. The truck left, and it left full. Yay! And so now you can see the percentage of fill time will start to drop, like you just saw. Okay? All right.
You could build this simulation in Erlang very easily, and it's been built the exact same way that you would.
Yep. So let's jump out of that and go look at what some code looks like for this. So this is the code that you just saw running. So I just picked a log normal distribution just because it's slow to calculate. A triangular distribution would have been better for the simulation. But you can see, first off, if you look at the top where it says line 16, we are not using objects. We're not using classes, we're using enums. And Swift enums are very interesting in that they are used both as you would think of a C-style enum and as a namespace. And so we can put functions in them. These are functions, not methods. And we have selected smallest is better, right? We want to use small amounts of memory as possible. So there was no need for the object overhead, both in size and speed. So we selected enums. And you can recognize, hopefully, you all recognize some of these functions. And so we have a gen server behavior that this gen server is going to implement. And we have two API functions at the top. Some of them, again, you'll probably recognize. And then we go into the define functions that are not going to be implemented for you at all, but they will be required. Okay, and we don't need some of these. There's a triangular distribution down there. So that's what a gen server looks like. Here's a state machine. Oh, let's go look at a simpler state machine than that one to begin with. We want, where'd it go? Get that one up there twice. There we go. Here's a loading dock. And you can see, again, we're implementing a gen state update behavior. And we've got some API functions, and then the standard built-in functions you have to implement. And it's been a lot of fun doing this. Honestly, it's been a blast. Event managers. So here in my start manager, which is an API function, that we wrote just for this, we're putting together a list of event handlers, which are just closures. And then when you call, the event managers notify, off it goes and executes and distributes them to everything like an Erlang event manager would. And then we get to person, and here we're switching on state, and you can see we're using the Erlang tuples, or the Swift tuples to switch on, and using the other part of enums, which are the standard declarations. So that dot boxing and dot loading comes from the enum that we've created. Yeah, so this is the way this code looks. I think it's looking familiar. It looked familiar to me when I was writing it. So part of the purpose of this library is to help bridge people from Erlang, or from Swift over to Erlang, to get them thinking in a better way than they're used to thinking. And the second part of it is to make every app on every device potentially a node. And so that's what we're working on. That's what we're going to hit. That's what we are going to do. And by we're hoping it's not just us.
Yeah, welcome contributions. Doing a lot of work, like I'm doing a lot of work to try to make it easy to contribute to the library. I went to Benjamin's talk. It was good. And hopefully it's, easy to understand, easy to jump into, and like eminently exciting. I thought that just the idea of it to me, I find just like vibratingly exciting. what you could do with this. But yeah, let's hear some questions real quick.
So is the idea to introduce people to Erlang or switch away from Erlang?
No. The idea is to, there's a gajillion Swift developers out there, right? iPhone developers and Android developers, all kinds of places. And we want to bridge them over to Erlang. So let's get them addicted to doing this on their device, and then when they go to do the back end, say, well, why would we do it any differently, right? That's where Node came from, right? Well, the front end's in JavaScript, why don't we write the back end in JavaScript? And then from Node, we got async await, which flew back out into the front end. And we've been paying the price ever since.
I think you could state that a different way. Well, no, like, because SwErl is a fully featured library. I think it's useful and good to use. And I think having something that can do user interfaces and mobile apps and smart devices is a natural extension of the Erlang ecosystem from where we are. And it will, like, because it is Swift, it will bring in expertise in the subject matter to our community, right? That none of us know how to write a user interface. We need somebody else to help us with that. And the Swift developers absolutely do. Like it's a way to bridge some communities. It's a way to get more people talking about Erlang, and we're going to be talking about Swift doing this. And hopefully we end up with an ecosystem that can do more than what Erlang can do right now. You know, using languages for the tools, or using tools and languages that are good for the problems they're solving. Yeah.
Hi, so I'm coming at this from more of an Elixir background with like dabbling of Erlang in there, and I'm kind of curious, when I'm writing the Swift for this, ideally it sounds like we're trying to provide an experience that feels a lot like writing your normal like Erlang code, is kind of making that transition easier. One of the things that we make heavy use of obviously is like pattern matching and especially recursion. Is that something that tends to be I'm unfamiliar with Swift as a language. Does it have good affordances for that? Is that something where,
Yeah.
when we write our things, we can expect like TCO to happen properly and whatnot?
So
I can take that one.
No, go ahead.
So Swift is not as good at it as the Beam languages, okay? State that flat out. However, it does do pattern matching. You can see it here in the case. The syntax is different. You cannot, this is what the documentation says. Decomposing tuples is not currently allowed directly in your function declaration.
And that's a pretty major drawback of Swift right now.
Yes.
There are things that can be done about it. Like what I have observed is that the pattern matching and recursion tools in Swift are quite robust generally. Notable exclusion there, and also quite extensible. If a little unwieldy, I think sometimes you're typing a lot more characters than you want to when you're writing SwErl. And I have been looking at there's a pattern matching operator, it is extendable, right? And we could extend it and do some type aliasing to make that safe amidst other Swift applications. Like, yeah, the library has to be usable, right? And I think right now, it's pretty good. I think you can write code in it, and I think there are many, many things you can do to optimize the programmer user experience of the thing from here.
We specifically didn't want to, when we were talking about what we wanted to accomplish before we started to present this, we did not want it to be complete, because this is way too big and way too important, in our opinion, for two people to do. It needs a lot more input, it needs a lot more thought, it needs a lot more community behind it in order to make it what it really can be. And just two people sitting around talking about it is insufficient. So we're actually begging that there's some people in here that would like to contribute to this and become a robust community. I would love to take this in a more complete form to a Swift conference and lay it out in front of them. That, I think, would stun some people.
Yeah, that'd be the goal. Please.
Yes.
So one of my favorite Joe Armstrong quotes is actually him asking what becomes possible when every device is an Erlang node. You're kind of gesturing at this world. So kind of stepping outside of just SwErl as a Swift implementation, what do you think is made possible in this world where everything is running something like SwErl and able to communicate?
Love that one.
You have to give me this one.
Oh, okay, all right.
Excellent.
Go ahead.
So about like 3 million things on a big spectrum, right? Like the obvious thing is that there are apps that are like hugely networked with all of the other same instance of that app, and a server is involved, and the programmers doing it like have to deal with that manually with sockets and whatnot, and Erlang would make that just like, SwErl makes that completely painless, which does beg a question that I am hoping to hear. Somebody figure out what's wrong with that I just said, okay? Okay. But even in like a more local sense, like there are so many applications that are your watch and your phone are linked and your Apple Visor Pro or whatever, right? We have all of these devices that want to be behaving on the same, like in the same context, on the same continuum, right? And having your phone and watch act in an Erlang distributed system just as if they're the same computer for your application, that's an extremely exciting thing to be able to do. No longer will you have huge synchronicity issues. You can take care of it automatically with the features that Erlang has. And you may have noticed that that's just like native Swift on both ends of that. That is what SwErl is trying to achieve, is a full implementation of all of Erlang patterns to the degree that they can be completed. There are some exceptions. In Swift. And even just like locally, I built a web app once. I don't want to do that again. And like, you know, I had a button over here that needed to affect something over there, and there were other buttons that affected that thing over there as well. And I wanted to separate the concerns properly, and I had to spend hundreds of lines writing what should just have been, you know, button 1, sending a message to that graph process over there. It works extremely well for building a user interface. It works extremely well for a local distributed system, just your computers that you own in a trusted Erlang environment. That's a hint at the question you should be asking.
And in addition to that, I specifically picked simulation for a reason for this demo. If you can simulate using a library, you can write a game with that same library.
That's true.
Because simulation and games are almost exactly the same thing. If you can simulate this using these types of structures, and then we add in the node portion of it, now I can do remote command and control. And I'd like you to imagine remote command and control over a physical device using Vision Pro or some other headset. So you can actually see what that large physical or small physical device is doing. I think we're pretty much limited by our imaginations on where we could take this. We could have a watch that we are wearing controlling the nerve stuff in our house really easily without going through HTTP, which is a very slow, very wordy protocol. So there's lots of things. I think we're out of time. But we'd be happy to talk to anybody and show anybody more, even the rock underneath code.
Yeah, the question you're supposed to ask is, what about like Erlang's security, right? Is a trusted thing? So come ask me that.
Great. Thank you so much.
Thank you.